here, zoom in on this a little bit, we can see that on the vertical axis here, for each of these individual diodes, we're going to have a certain voltage and a certain current leading up to the extinction. Okay, so the extinction happens not because of reverse bias voltage, but because we've reached that point where the electron has enough oomph to get over that bump. Okay, and so, what you're going to need to do then is plot something like, here this is current versus voltage. So you need to do this for each diode. So we've got 7 of them, so we need 7 of these plots. So it's going to look like this. The current is going to be higher when the voltage is higher, but then we get down to the extinction voltage where the current has gone to 0 and there's no light. And then it'll stay 0 all the way across. So you'll have some points up here that you'll be plotting. But then one thing that happens that's a little bit funny here is that down near the bottom, it may not just perfectly intersect with the horizontal axis, but it may take a little squiggly thing and do that. And so if you're seeing this in your data, this needs to be explained and what you're going to do about it. Are you going to, so one question you can ask yourselves is, are you going to choose this value or that value? And explain why. So it might make sense to extrapolate straight down, but maybe there's some complex interactions taking place right near the extinction voltage that are specific to the physics of what's going on in that p-n junction. So one thing you might want to do is figure out the voltage here, but maybe use some error bars, indicating that maybe you try this value and you try that value, and that gives you a slight spread in your result. So in your plots, I want you to use error bars. But the actual way in which you analyze this and the decisions you make are up to you. But I think that you definitely do need this kind of a plot for each one of these things. And so each one of these, as you can see here, this is for the red one, this is for the green one, blue one. They're shifted a little bit. And so that corresponds then to the fact that we have to have more voltage in order to overcome the impetus for a smaller wavelength. So as 1 over lambda goes up, that means that lambda goes down. Okay, so as lambda goes down, the energy goes up, and so you need more and more voltage to get over that peak. And at that point when you get over the peak, then the photon that's released is going to have a difference in voltage, and that'll result in a higher frequency photon, okay, or a lower wavelength photon. But the assumptions that we're making here, your error bars aren't just about which of these choices of 0 voltage you're going to want to select. It's also about assuming that the energy lost during the electron's interaction is the same for every semiconductor. Is that a good assumption? Well, you don't know what this value is, and so you can't just go through and solve this thing for Planck's constant for each of the data points. You go, I'll just solve this. This is n equals 1. And so I'll just say that EV equals hc over lambda, and I've got Planck's constant, right? No, because there's this energy loss term that has to be considered. And so my son took this class for me about 6 years ago, and usually his results are pretty amazing, but I didn't like what he did on this lab. Let me just show you what he did here. He took each of the different values for the voltage, and he just solved it using this equation, and he solved for H. And look what he got here. He got 14, 23, 11, 22, 55% error. Okay? And so I think a lot of that error is due to the fact that he wasn't considering the shift that is caused by the energy that's lost. It's not like the energy that you lose in a filament of a light bulb, because that has to go all the way up to the black body radiation temperature to radiate, and so you're really losing heat there. You're not losing nearly as much here. Again, that's why the LEDs are so much more efficient. But you're still losing enough to mess up your results. And so I think the best way to do this is with a plot, something like this. It doesn't have to look exactly like this. You could plot voltage versus frequency if you want. But let's see. What he did here, I liked. Here, he just did the other way around. 1 over lambda versus voltage, and he plotted a straight line. But here, I don't like this, because here he was doing all the individual values, then trying to calculate those error bars, but his error bars had nothing to do with the energy that's lost. And so this plot here doesn't really make a lot of sense to me. And then this scatter here comes from the fact that there's an infrared one too, and you can't see the infrared, of course. And so I think that one's less accurate. And that's probably why you may not get as good results for the infrared one, is that you can't see when it's about to go to 0, and because you can't see it, I think maybe they don't calibrate it as well when they're making the infrared LEDs. Okay, so those are a couple of things then to consider. Are there any questions so far? All right, let me, there's a couple other things on diodes that I wanted to show you. This is if it's forward bias, but what if I reverse the direction? Make it go this way. So here's our P, there's our N. Okay, and so positive, this is the positive side of the battery, that'll tend to attract negatives on the inside. So the insides will go across like this. And then, because the electrons tend to want to go this way, the electrons will slam up into this edge here. But electrons moving this way is the same thing as holes moving this way. So what we've got then is a depletion region, which is like the Grand Canyon. So that means it's a huge insulating gap, and so that stops the flow of electrons. And so there's no current flow. So that's what a diode does. And so oftentimes then we would write it like this. So that current can go this way, but can't go that way in the reverse direction. Or this way, depending on which way the current is flowing in this particular. In this case, the current would be going this way, and it couldn't go back in the opposite direction. So that would be what would be represented by what I have here. So this allows for the current to go this way, but not back that way. So if we plug this into an AC source, we have our diode in here. And usually we put a resistor in here because high voltages can damage diodes. What would happen is that you cut out half the signal. The signal then would look like this, and you've lost half of it, but what's left, the electrons would always be flowing in the right direction. But wouldn't it be cool if you could save the whole signal? And so that's what 4 diodes put together does for you, is it's called a full wave rectifier, and it saves the whole signal. Okay, so here's your AC generator. Here's the so the diodes are oriented like this. And so if we have a positive part of the signal, that'll go through this way. It can't go that way because it can't go against that diode, so it goes this way. Can't go that way, so it goes through the resistor. So this would be our measuring device. When it's negative, it'll go through this way. Can't go through that one, but it can go through that one. Then it can't go that way, so then it goes through. And so that saves the bottom part of the signal. It's pretty clever. So that's one of the techniques for turning AC into DC, is to first take the absolute value of the signal and then smooth it, like with capacitors and inductors and stuff. And that can give rise to depending on how good your converter is, can give you a fairly stable DC-like signal from an AC source. Any questions about that? And now a transistor is 2 diodes put back to back. So if you had, like, for example, a PNP transistor, put the 2 diodes back to back. Let's say you have a signal that's coming in like this, and then you've got some big battery in here that can amplify that signal. Okay. Then what will happen is the signal can go through this way. That jumbles up the holes, and that decreases the resistance through this gap and allows for a huge amount of current to flow through this bigger loop. Okay, and so you can take a smaller signal like this and turn it into something that looks just like it, but has quite a bit more voltage. And so the essence of this thing comes from the fact that you let it flow through this part of the path like a diode, but then that is like a blender that gets all the holes or the electrons churning around in here and allows for a larger amount of voltage. I should probably put a voltage in here. Figure out where the voltages go. There's a lot of different versions of this, but that allows a bigger voltage to flow. When a smaller voltage and current flows through here, then that point would map into that point, this point would map into that point, etc. You have a transistor. Okay, so let's just go back now, and I've got a quick little video to show you on the operation of diodes.
I used to spend dozens of hours every single week proofreading. I was constantly fixing run-on sentences, unclear syntax.
Diodes have numerous